Electricity, first and foremost, is the flow of electrons. And electrons are the charged subatomic particles that envelop atoms, right? For these electrons to flow, they need to flow through something. And that something that they flow through is called a conductor. So the first thing we're going to talk about is a conductor versus an insulator. So conductors allow current to flow through. So electrons can flow through a conductor. An insulator, electrons don't flow. They do not flow through an insulator. And so these are not, it's not a binary situation. These are a spectrum. There is everything in between something which is a theoretical perfect insulator and a perfect conductor. And the difference between these is how much they resist the flow of electricity. And so then, somewhere in between, you will have something known as, well, in here we have this spectrum, right? There is everything in between a perfect conductor that allows electrons to flow with no resistance, no impedance to those electrons moving through a conductive medium, and something that completely stops the flow of electrons. The best insulator that we can have pretty much is a vacuum. Well, that's not completely true, but something that electrons don't want to flow through. Nothingness, vacuum space, is pretty darn good as an insulator. And in this middle area, we have materials of varying resistance. And so what defines the spectrum is resistance. So now we need to talk about resistance. Now that we've established that there is an ideal, a platonic ideal on either end of our spectrum, and that is the spectrum of resistance. So now, how does resistance influence how electrons can flow? And to do that, we need to bring in a few other vocab words. So you might be familiar with some of these just from using various devices. The first term we're going to talk about is voltage, and then we're going to get to current, and then we're going to talk about how voltage, current, and resistance all interrelate with one another. So first of all, voltage is a potential energy. Voltage is defined by so in physics, voltage is called voltage potential, and because it's a type of potential energy, we can think about it in terms of gravity, right? If I take an object and I have tape stuck to the bottom of my object here. I'll just use the tape. If I take an object and I drop it, there is a certain amount of energy that's going to be impacting my hand, right? Because the height difference between this object and where it lands will, as it falls, it's going to convert that potential energy into kinetic energy. Voltage potential is about charge. It's about how much pressure there is pushing electrons from one charge level to a lower charge level. So just like I can look at the relationship between this object and this surface of my hand where it can fall to, I can change that distance and increase the relative potential energy between the object and the surface to which it can fall. The same is true with voltage. It's a relatively defined differential between charge. But for our purposes, because we're just getting started learning about what electricity is, we are going to think about electrons as, we're going to use a metaphor of water and flowing water to describe how electrons behave. And we're going to use gravity as our metaphor for voltage, or rather the influence of gravity. So going back to the paper here, I'm going to start out with just a hill. And on top of this hill, I'm going to put a hot tub full of water. And on the bottom of the hill, I'll put my second hot tub that does not have any water in it yet. In this metaphor, we can think of this difference in height. This is our voltage. And so right here, right, there is a difference in height here. There's a difference in voltage between these two positions, but as this exists, there's no flowing water, right? It's just, there's some water up there, there's a place down there, but there's no flow. In this instance, yeah, go for it. No. The steepness of the hill does not affect the voltage. It's the overall, great question. It's the overall difference in height, which is actually the same way that water works. It actually, if you had a hose full of water and you put it at one angle versus another angle, that slope doesn't actually affect the what's called the head pressure in water. It gets more complicated because then what's affecting that is like the diameter of the hose will change how it works with that, because you're going to have a longer hose if it's at a shallower angle. We'll get to that, but great question. Oh yeah, so in this situation as we have it, right, we just have one body of water and one vessel that are at different heights, but there's no connection between them. This is a great metaphor for static electricity. Static electricity is voltage differential without flow. Right, so static, stasis, nothing's happening. Electricity, some situation with electrons. I don't know if any of you have ever used a Van de Graaff generator, maybe in science class in elementary school or something. The thing where you touch it and all your hair stands on end. If you have straight hair. But what that's doing is it's building up static electricity. It's building up charge without that charge having anywhere to go. So then we just are having static repulsion forces, where we might know that like charges repel and opposite charges attract each other. So a positive and a negative charge will pull towards each other, and alike charges will actually push away from one another. So what's happening with a static electricity, like a Van de Graaff generator, when your hair stands on end, is all of your hairs have electrons on the surface of them, and they try to get as far away from each other as possible. So instead of them laying down flat, they all try to spread out evenly. Which, interestingly, if any of you have ever been near a lightning strike, the same thing happens right before lightning strikes. Anyway, back to our water metaphor. If we want this water, this electricity, these electrons to flow, we have to connect these two vessels somehow. So we will hook them up with a hose of some sort. And once we have this connection, then water will begin to flow down there. So just thinking about how this behavior of flow is going to work, let's now talk about this hose. So let's zoom in on our hose here. Our hose has some manner of cross-section, right? The hose can be really small, or it can be a fire hose, or it can be like a massive oil pipeline, right? So we have a variable to think about in this whole situation, right? Which is the cross-section or size of the hose. And as you might be able to imagine, that difference in the different possible sizes of that hose are going to, they're going to affect how quickly that water will flow between these two tubs, right? If you can think about it, if you have like a bubble tea, like a boba straw, one of those big straws that's like this big, it's very easy to drink through that, right? Versus if you take one of those teeny tiny little straws that are for like stirring your coffee, trying to suck through that, you get a lot less flow because the nature of that cross section is going to resist the flow of fluid differently depending on its size. This is our metaphor for resistance, is the size of our tube. And in electricity, the size of the conductor actually does have a direct relationship with its conductivity. The thinner your wire, the less, the more resistance it's going to have, the fewer electrons can flow through it in any one spot. And conversely, the larger your conductor, the more electrons can fit through there. But that's not the only concern. There's also material. There's differences between materials. So like graphite, like what's in a pencil. Oh, that's terrible. That was very invisible. Like the graphite that's inside of a pencil lead is conductive. It's not very conductive, but it can conduct some electricity. Versus like gold is a really good conductor, and if any of you are audiophiles or musicians, you might be familiar with this, that like plugs for instruments, the expensive ones are gold plated because that gold is a really good conductor. And then you get better audio quality. Or if any of you build PCs or have ever looked at high quality electronics, there will be gold in there. In fact, people reclaim gold from like e-waste to extract that precious metal. But yeah, so it's not just size, it's also material, which we're going to not talk about material differences in our metaphor. We're just going to talk about how much water can flow through our hose. But, oops, sorry. The cross-section of our hose is not the only thing that's coming into play for how fast our water is going to flow, right? The voltage also is going to determine how fast the water is going to flow, right? If I, for example, instead of having these one of them on a hill and one of them down in the valley, if I had them both at the same level and connected them with a hose, right? There's no pressure to make this water flow either way, right? So we can see if we go to the extreme here, where there is no voltage differential between the two, then there's not going to be any push. There's not going to be anything to make that water move. So our the resistance of our connection and the voltage are going to influence that flow. And that flow is, in electricity terms, what we call current. And if we go to a very like low level understanding of this, current is really how many electrons are passing any point at per second. It really is the amount of actual tiny subatomic particles that move past or move through a conductor per unit of time. Okay. So now that we have these three concepts of voltage, current, and resistance, now we're going to talk about how those three characteristics of electricity relate and interact with one another mathematically. But before we do that, let's talk about some units. So voltage, oh, my pen is running out of juice. Voltage is measured in volts. Exciting. Resistance is measured in ohms. And current is measured in amps, which is short for amperes. I'll write that. And these all have symbols associated with them. And this is V, R, or theta, omega. And amps are measured in, their symbol is I. But these are our symbols that we're going to use to represent voltage, resistance, and current. And so these interact in what's called Ohm's law, which is V equals I times R, or V equals IR. You're not going to need to worry about this with a lot of the components, but with some of them you will actually need to do a little bit of math. Because, just from the metaphor, right, if we change the relative distance and height between these things, that's going to make more current flow, right? There's more push. And if we change that cross-sectional area of our hose, that's going to influence the current flow. We can intuitively look at this and see the relationship here. So just let's take a second to look at that. Right. So if we, here I'm gonna retract my paper a little bit real quick. And write our Ohm's law right here again. I'm going to get rid of this pen too. Excuse me. So V equals IR. So in this situation, right, unless we're bringing our excavator machine or backhoe or whatever to dig a new pit here or pile up more dirt, this voltage differential is not going to change. Right? So if we have that as our stable thing, right, then this unit here, our voltage is constant. We're not going to be altering that. Even if this was empty or almost empty or whatever, the voltage is constant. So that means that if we change our hose size, right, like if our resistance decreases, right, if the resistance decreases, meaning the hose gets larger, then that means that the current mathematically has to increase. Otherwise, voltage will change, which can't happen, right? Changing our hose size isn't going to make this hill bigger. That doesn't make any sense, right? So just looking at this formula, or this law, if resistance decreases, that means that the flow rate has to increase in order to preserve the value of our voltage. Now, similarly, if we had, instead of having this on a hill, if we had our tub on like a forklift. Let's see if I could draw a forklift real quick. Close enough. We had our tub on a forklift, and we could raise and lower this, right? And our hose was of a constant size. Then now, resistance is going to be preserved, right? If our hose is going to stay the same size, and we're going to increase or decrease our voltage differential. Right, we have our two tubs connected by a hose, and this can move up and down. Now what we'll do is we can solve for R, right? So if we solve for R, what we'll do is we'll divide both sides by I. That'll cancel out. R equals V divided by I. So now, if our voltage increases, so must our current in order for resistance to stay the same. Let's throw some some dummy numbers in here just to see that happen. So if our voltage starts out at 1 volt and our current starts out at 2 amps, right? If that means that R equals 1/2. If our voltage is 1 volt and our current is 2 amps. Now, if our voltage goes up to 2 volts, then for this to still equal 1/2, then our current is going to have to equal 4 amps, right? For this to remain at a value of 1/2, because we're not changing the size of our hose. We're just lifting up a tub of water. So, hopefully that makes not only intuitive sense, but mathematical sense, where we have this interrelated situation between voltage, current, and amperage. Oh, sorry, voltage, current, and resistance. Sorry, say that again? Well, we're not even going to touch calculus, luckily. But good. So, what we do with electricity with the Arduino, as I said before, like basically what we're doing is we're these pins, as they're called, they're either going to be used to receive electricity or put electricity out. And we're going to influence the characteristic of that electricity. Or read what's happening with the electricity that's coming in. So let me see how we're doing on time. Okay, we're about a half an hour in. That's good. Okay, so the Arduino. Let me go back to drawing. We'll talk about some things that the Arduino can receive. We'll talk about what the Arduino can read. So moving back to our hot tub on the hill. We have imagine now that in line with our hose, we have a valve that I can turn on or off, right? This is going to be essentially the same thing as changing the size of that that hose, right? This is what would be known in this valve that can turn electricity on and off in a gradient, is like a variable resistor. And one thing that we have in the kits that we might be familiar with seeing, at least, is, and something that you've definitely encountered out in the world is, I can't tell if that's fuzzy just because of bad zoom. One second, that's as good as it gets. This is a little knob that can turn. This knob is a variable resistor, but specifically, this is known as a potentiometer. And so just looking at this word, let's break it down. So meter, like measurement. Potentio, that sounds familiar, right? Because we were talking about voltage as a potential energy. So I'll just write voltage potential. This potentiometer is something that we use not only to vary this flow of electricity, but what this does is it actually splits that flow of electricity. So I'm going to draw a second hose coming out. And here would be our Arduino. Just a quick, don't plug your Arduino up to the water. This is just a metaphor still. But what we're doing here is we are diverting some of that flow, right? So if we have some water flowing down into our tub, that means that there's less water flowing into our Arduino, right? So this is essentially how knobs are used in electronics. What they're doing is we have, I'm gonna move away from the water for a second. We have a 5 volt or whatever our power source is. The Arduino is generally a 5 volt device, mostly. That 5 volts is then split into 2 different paths. one of which is going to pass through a resistor. This is the symbol for a resistor, and go to ground, which this is the symbol for ground. And if we just, for just a split second, go back to the water, right? In this metaphor, ground is as low as you can get. Ground is defined as 0 volts. And that's partially for the metaphor and partially because the ground, the actual ground below our feet, is, by our human definition, by our earthbound definition, neutral, right? It is just the shared common thing that we all are standing on, and it has pretty dispersed, even charge in it. So that's just what because we live on Earth, the ground is defined as neutral, as 0, as ground. And if you are in England more, they'll instead of saying like ground, they might say earth. So if you're ever looking at electronics stuff and they say, oh, this is the earth, ground and earth are interchangeable, meaning the defined 0 volt basis on which we define other voltages. Okay. So we have our ground, which is 0 volts, and we have, we'll say 5 volts and a resistor. And we have a second resistor, and then this is going to go to some pin on our Arduino. And I'm going to specifically write an analog pin on Arduino. And so what happens here, the potentiometer is going to increase one side as it decreases the resistance of another pin. If you note, there are 3 pins on the potentiometer. There's 3 pins, and one of these is going to be connected to our 5 volts. One is going to be connected to the ground, and the center one is going to be connected to our Arduino. And just the way it works is inside of this, there is physically a piece of stuff here that has, on one side, 5 volts, on the other side, ground, often shortened to G and D. And this material is a resistive material. And so as the electricity flows from high voltage to low voltage through that, like this one pin comes out and it's connected to 5 volts, one pin comes out and is connected to ground. The length of this resistance, of this resistive material, influences its resistance, right? If you imagine, like we were talking about like the little tiny straws used for stirring coffee, right? If you imagine one that was this long, blowing through it, it's going to be difficult. But if you cut it in half, it's going to be half as difficult. It's going to be twice as easy. So the length of this resistor influences how much it resists the flow of electricity. So, excuse me, inside of that potentiometer, we have this resistive material, and then the knob, as we turn it, is actually connected to a little wire that turns inside of there. And it can make a connection here, or here, or wherever in there. And that wire is connected to that center pin, which we call our signal pin. And depending on how far you've turned it, there will be a shorter path. Sorry, I was blocking that a little bit with my hand. A shorter path between the 5 volts and the signal pin, or a longer path through that resistor, which is going to influence the resistance, which is going to change the amount of electricity that's going to that pin. I want to talk very briefly about another topic, which is how the Arduino can output electricity. This one's a little bit less intuitive, maybe, but it's something that we've all experienced looking at LED illumination. All right, so we've talked about 5 volts. We've talked about voltage. We've talked about ground. We've talked about 0 volts. So now what we're going to do is we're going to look at how we control LEDs. But first, let's write down LEDs. Let's get into what an LED is real quick. So LEDs are light emitting diodes. And so y'all have probably seen LEDs. Like I don't know if any of you are sitting in a room that's lined with LED strips right now, flashing rainbow colors, or if you have a gaming rig that has like backlights on the monitor or whatever, or if you've seen that on the internet. But what those are LEDs. Those are light-emitting diodes. And what a light-emitting diode is, the electronic symbol for an LED is this. So this little picture you might see if you ever look at an electronic circuit diagram. This is an LED. And these little lines here, that's the light coming out of it. Those are little arrows. And a diode is a one-way valve. Electricity can flow through that way in the direction of this arrow, but it cannot flow the opposite direction. And unlike old school bulbs, right, that have the filament in them, unlike these, how much light comes out of an LED is not related to how much voltage goes into it. With an old school light bulb, if you put more voltage in, more voltage equals more light. That is not what happens with an LED. You put in more voltage, what you get is fire. You get it'll burn out. So the way that these LEDs are controlled, the way that we get all of the different colors out of these LEDs and is through illuminating 3 different LEDs. We have a red, green, and a blue LED. Same way that we think about color on our screens when we're dealing with red, green, and blue color values. We need to change that illumination level of those different channels. But because we can't just directly control the brightness by changing the voltage, we need to exploit the way that we perceive, or the way that the eyeball works, and the way that the brain can work. And that is by using pulse width modulation. And so what is pulse width modulation? So big P, pulse width modulation, or PWM. Pulse width modulation is changing the percentage of time that that power is being supplied. So if anyone has anything that has any LED lights nearby, what I want you to do is I want you to take that LED and move it quickly. Or if you have ever like ridden your bike past a bodega or whatever, and like the LEDs that are in the window of the bodega, you can see that they kind of like have this trail, streaky nature to them. What you're seeing is the PWM of that light source. So what's happening is those lights, if you look at them straight on, they look constant, but if you move, what you're actually able to see is that the lights are flashing on and off very rapidly. And what we're doing here is we're going to change the ratio, or the percentage, whatever way you want to think about it, of the time that it's on versus the time that it's off. So if it's on a larger percentage of the time, it's going to be brighter because there is actually more light coming out of it over time, but at any instant that it's on, it's at constant brightness. So turning that into a graph, right? If we have our graph with time on the bottom, and we'll just keep it easy. We'll just say on and off for an LED. If we have an LED that's constantly, if we just are supplying power to it and we aren't using PWM, what we're going to see is it's going to be on, like the graph will just be a line up here. And same, if we turn it off, we just have a line down here. If we turn it on, off, on, off, on, off, where it's the same amount of time that it's on as it is off, we'll see a graph something like this, where this amount of time that it's on is equal to the amount of time that it's off. This is known as a 50% duty cycle PWM. Duty cycle is the term for the ratio of on to off. 50%, it's on 50% of this wavelength of this cycle, right? So we have an on and an off, and that on and off comprises one cycle. If we had a graph that looked like, I'll just say time, and on and off again. If we had had something that looked like this, where, let's just imagine that I drew this perfectly, where this amount of time that's on is 1/3 of the amount of time that it's off. This is a 25% duty cycle. Because the way the cycle here, right, goes until our next pulse. And if we just look at this, there's 1, 2, 3, 4. So the ratio of on to cycle length is 1/4, right? 1/4 of the time, it's on 1/4 of the time. 25% is the same as 1/4. right? 25 over 100 is equal to 1/4. This is going to be 1/2 as bright as this because it's on for 1/2 as much of the time. And if we had one that went like, that's not legible, sorry. If it's on most of the time and only off 1/4 of the time, then this would be a 75% duty cycle if I drew this perfectly. So this we can do with the Arduino, and this is what is controlling, the brightness of those LEDs that you might see in your room or at the bodega. And so if we go back, remember, so it's pulse width modulation, right? We have a pulse. These are our pulses. We're changing the width of the pulse, right? Modulation means to change something. We're modulating the width of the pulse. Pulse width modulation, PWM. There's two more things I want to get into, and then we'll have a little bit of time for a lab session for you to work on your meme projects. But the two things that I want to look at are one, implementation of Ohm's law, specifically with reference to an LED, and then yeah, that actually we may stop there, but we'll see how we're doing on time. So as we said, Ohm's law is V equals IR. Voltage is current times resistance, and let's start there, and we'll talk about a characteristic of LEDs. Let me just see that. That's a little better. Okay. All right. So we said that voltage equals current times resistance, and we talked about how there's we can see the mathematical relationship here. So if resistance goes down, current will go up if we have static voltage, right? So LEDs, which we may remember the symbol for, LEDs have an interesting characteristic about them, which is when they turn on, their resistance approaches 0. Like it gets teensy tiny, almost nothing, almost no resistance. And if we look at Ohm's law, if resistance is 0, so let's plug some numbers in here. Let's say V is 5 volts equals IR. If resistance is 0, then equals I times 0? Wait, we can't do that. Anything times 0 is 0. That's not going to work, which means, so it doesn't get to actually 0, but it's very close to 0. That means that current would have to increase approaching infinity, which we definitely do not want. Infinite current is bad. That's too fast of electron flow. It's not possible. But basically what that means is that if we allow the LED to just be powered of its own accord, it's going to let so many electrons through that it's going to burn up. Has anyone heard the term magic smoke when talking about electronics? Has anyone heard this term before? So it's kind of an electronics person joke, where if you're doing something with electronics and something burns up, when things burn, there's smoke. The joke is that when something burns up and it stops working, that's because you released the magic smoke that's held prisoner inside of the component. So if your LED burns out and a little puff of smoke comes out of it, it'll no longer work because that smoke was in there making it work. It's corny, but it's if you get going with electronics, you will hear someone refer to the magic smoke. Yeah, exactly. Yeah, it's a fun way to say I screwed up. But so because we want to keep that magic smoke in there, we want to protect our LEDs. So when you get an LED, which I have some of right here in front of me, I'll switch my camera over. So here's a little LED, and I'll just zoom in on it real quick so you can see it a little bit better. There's our LED, and here's where the magic smoke is in there. So LEDs, when you purchase them, they will tell you what kind, like the characteristics of the electricity that this component will use. The ideal voltage and current of this component. So just continuing up here. A common, man, that is really not sticking. 1 second. There we go. So a common red LED might want 3 volts and 20 milliamps. So remember, amps or amperes is the unit for current. Milliamps is 1,000th, like millimeter, right? Milli is 1,000th. So this is also equal to, if we move that decimal point 3 places over, 0.02 amps. And so this is the characteristic of the electricity that this LED wants to use. If our power supply is 5 volts, so let me just LED requirements, and this is our power supply. That means that we need to get a resistor in there that's going to use up some electricity to protect our LED. So a resistor is a component such as this that has a known resistance. It has a demonstrated amount of ohms. So like I have this book of resistors here that have all of these different values, so I can go through and choose which one is correct for the application that I want. And so what we do once we calculate a resistor value, come on now, then we can grab it from the book. But so here, right, if my power supply is 5 volts and I want to use up 2 volts to leave me with 3 volts left for my LED, I'm going to use Ohm's law, right? So we have Ohm's law, V equals IR, and we're going to solve for R, right? So V equals IR, we divide both sides by I to cancel this I out. R equals V divided by I. So if I have 2 volts that I need to use up, 2 for my volts, divided by my current, 0.02, and I'm going to pull up the old calculator. 2 divided by 0.02 equals 100. So 100 ohms. This is I'm going to have a circuit where I have my 5-volt power supply, a resistor of 100 ohms, and then I can have my LED, and then ground. So what's going to happen, this resistor is going to manage the flow of electricity. This is going to be, we're going to use this resistor to set that hose size that's going to let those electrons through, so that now when this component turns on and it gets its very low resistance, it's not going to burst. Well, it doesn't burst. It doesn't burst into flames. It just kind of just stops working. But this is an implementation of Ohm's law that if you ever use an LED, you're going to want to use. And this is something called a current limiting resistor, because remember we talked about how when the resistance goes low, the current increases. So this resistor will limit that current flow. So I'll just write that down next to it. Current limiting resistor. Yeah. So there's a nice implementation of Ohm's law, and remembering that with just a teeny bit of algebra, we can solve for the different variables in that equation. Okay, I think I'm actually gonna. Let's see. I'll say one more thing about the way that Arduino deals with voltage, and then the rest of the class will just be some lab time for meme projects. But so the Arduino can both do output and input. So the output, when we when we're outputting electricity, we're going to call this writing. And for for input, this is reading. Right? Reading, you input knowledge, knowledge goes into you, and when you write, you're exporting knowledge. So like in and out, that should be hopefully a logical relationship there. Arduino can do two types of each of these, analog and digital. Digital, as we are hopefully familiar, digital is like a Boolean. So it's a yes or a no. It's digital meaning like the binary digits 0 and 1. So that means that for input, for digital input, just go. We have digital and analog here, and we also have digital and analog for reading and writing. So digital, we have true or false, aka high or low, meaning that this is going to determine whether or not there is power or not being supplied to a pin. So this will be, it's 5 volts or not. For analog inputs tell us how much electricity. So this will tell us on a spectrum 0 through 5 volts. So if I plug in a power, like a source of power, and do an analog read, this is going to give us a value between 0 and 1023. So in the same way that with with our work with, our work with P5, right, we can see the position of the mouse, right? That's kind of like more of an analog type of data in this sense, where we can see a spectrum of values, right? And it's turned into a numerical value, right? Similarly, the Arduino will take, if it's plugged into an input that changes the amount of power that's being supplied to it, it's going to turn that into a numerical value between 0 and 1023, where 0 will match up with 0 volts, 5 volts will match up with a value of 1023. If we are doing a digital read on that same input, it'll say that we are receiving low voltage until we reach a threshold, and then it'll say, oh, there's a higher voltage here. For output, digital is the same. There's high or low, meaning 0 volts or 5 volts. But that's coming out of a pin on the Arduino. And for analog write, this is our PWM, which in Arduino has a value of 0 through 255. So it has a lower resolution than the output, but both of them are, as we are familiar with, they are powers of 2, right? 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. So we have 2 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have an 8-bit number for output resolution. And a 10-bit input resolution. This isn't so important, but just I want to try to have you attuned to when you see powers of 2, or in our case, because it's a indexed at 0, we have 0 through 1023, right? But that is, there's 1024 values there. We have 1 through 1023, and then there's also that 0. So there's 1024 values in this range. So keep yourself attuned to powers of 2. And yeah, it's okay if this is a bit obtuse at the moment. We will play with this for real in our next class. But I just want you to remember, we have outputs and inputs, and for each of them we have digital and analog versions.